Erwin Schrödinger was a pioneer in quantum theory. He developed a thought experiment, now known as Schrödinger's cat, testing a popular interpretation of quantum theory, that an unobserved particle or system in two possible states becomes one or the other only when an observation or detection takes place. Schrödinger intended for his cat experiment to show the absurdity of the application of quantum theory to our everyday scale of experience. But quantum controversy has led to the development of the many-worlds theory, which takes quantum implications seriously on any scale, including Schrödinger's cat. I'll describe the theoretical background for Schrödinger's cat and my clock just briefly. One of the tenets of quantum theory is that particles and systems are inherently unpredictable, but their potential changes can be estimated by an equation called the wave function. When a predicted change occurs, one way or another, there is said to be a collapse of the wave function, and until the event occurs, the possible states being estimated are said to actually exist simultaneously in both possibilities, called a superposition. This is a strange counterintuitive belief. How is it justified? A wave function sounds like a description of a physical process, and quantum theory, being a fundamentally mathematical discipline, has not sufficiently examined the supposed physical connection. If the function had originally been called a curve function, not a wave function, producing a result called a collapse of the probability curve, which is what it really is, just an equation that will produce a wave-like curve on a blackboard, maybe a very expansive and expensive theoretical pursuit in quantum physics could have been avoided. Well, let's look at the classic example of Schrödinger's cat for how well it stands up to being considered from a physical perspective. This drawing provides a somewhat simplified setup. In Schrödinger's experiment, a cat is placed in a windowless chamber where it can't be observed, along with a radioactive piece of uranium and a flask or vial of poison gas. If the uranium decays, the vial is shattered and the cat is killed. According to many quantum theorists, until the situation is observed, the cat is in a superposition of states, both dead and alive. Only when the chamber is opened, when a collapse of the wave function occurs, is the cat actually either dead or alive. Quantum mathematicians will assure you that you are being naive if you don't accept this as a reality. I don't. You could call my belief physical, not mathematical. That just because two possibilities of the state of a system are calculated, the mathematics and the observation are of no actual consequence to the physics involved, on any scale. I want to show here that the cat theory is not just an absurdity for those who don't understand quantum theory, but that quantum theory is, at least in this respect, an absurdity that needs to be brought back into the realm of physics. Here, in this windowless chamber, instead of a cat, there is a clock. It is a special sort of clock. It only operates in a vacuum, so it is placed inside a canister that maintains a vacuum, allowing the clock to tick and to tell time. There is, as in Schrödinger's experiment, a piece of uranium, but no need of a vial of poison. In this experiment, if the uranium decays and strikes the vacuum canister, the vacuum is broken and the clock is killed. So what happens when the chamber door is opened? Is the clock suddenly transformed from a state of quantum superposition, from both ticking and not ticking, to just one or the other, and only then with the collapse of the wave function? What do the hands on the clock or the digital readout indicate? Will it always be the exact time that the door is opened when the wave function collapses? Of course not. There is no wave. There is no collapse. The clock says that it stopped at the precise moment the uranium decayed and broke the vacuum. You can repeat the experiment as many times as you like, and except in the unlikely event that the uranium happened to decay at the moment the experimenter opened the chamber door, the clock will confirm, or not, the estimation of the mathematical curve function, confirming whether it occurred within the range of predicted time to decay. Quantum theory is in need of reform and restraint. Today it investigates far beyond the study of phenomena so small they are impossible to directly observe. It is now concerned with multiple dimensions, multiple universes. It even aspires to understand human consciousness. Without bothering to criticize or refute Einstein's well-confirmed theory that gravity is geometry, quantum theory insists on treating gravity as a force, subject to quantum investigations. As a theory of quantum force, it would have to account for the massive ebbs and flows of the ocean tides. But yet the particle, the graviton, that would be responsible for mediating the stupendous, gigantic, super-colossal force moving all the oceans, that vast swarm of so-called gravitons required, cannot even be detected. It is utterly implausible, and it's entirely unnecessary to inject a quantum force into Einstein's gravitation theory, which works fine without it. Plus, the search for a unified field theory would be greatly simplified by removing a hypothetical gravitational force from consideration. Quantum theory is in need of reform and restraint. I've uploaded several physics videos on YouTube, listed below in the description. The most recent one is on black holes, and it hasn't been able to break through the dozens of well-established videos that appear on a search on the subject. I especially recommend the video which provides a simple graphic explanation of special relativity, which I believe gives the only clear explanation anywhere for how two observers can, in the same circumstance, observe the other's clock to be moving more slowly than their own. It also provides a clear and simple explanation for the speed of light being the ultimate and invariant speed. I hope you have a look. With regard to all you rascally quantum mathematical physicists, your comments are welcome and eagerly anticipated.